Hello guys, you're welcome to our lecture on the elliptic equations in 2D. We are done with the first two sections, so we are left with the last bit. And so this lecture is going to cover, I'll talk about some introduction to elliptic equations, and then we'll look at a model problem as we've often been doing, and then two examples to illustrate this. After that, we'll see that in solving elliptic equations you come up with sparse matrices, if you like. The coefficient matrices that you come up with are very sparse, and if the system is large, it's very inefficient to use direct methods. And so we'll move on to do something about iterative solutions to linear algebraic equations. We specifically look at the Jacobi method as well as the Gauss-Seidel method. And then we'll look at ways of increasing conversions using the so-called SOR iteration. And then I've put some sample MATLAB codes at the end of the lecture. Okay, so once we are done, you'll have some codes to take a look at. All right, so let's get right into our lecture. Now, unlike parabolic equations where we're looking at, for instance, the heat equation and looking at distribution of heat in a system, and then we got to hyperbolic equations which describe, for instance, the movement of a signal or wave. Elliptic equations describe the steady state of a physical process. So if you take the heat equation, for instance, after heat has moved through an object, say a metal plate, over time, allow this to cease, and after a long time, the steady state nature of that metal plate is described by an elliptic equation. So it is interesting to look at the final stages. It has important applications in physics in other areas. Now, the simplest model for elliptic equations are the Laplace equations and the Poisson equations, as you probably know already. Okay, so that's the famous Laplace, and that is the modified version of this, which is the Poisson equation. Now, note that the left-hand side operator, that is this guy here, this appears in the heat equation. All right, but you get this, for instance, the Laplace equation when the u dt here goes to 0, and so time is not involved. So in the case of the Poisson and Laplace equations or elliptic equations, you don't have time dependence. So that time dependence is removed, and all you have spatial dependence of properties. Okay, so that is on the elliptic equations. Now, often, if you have a domain, let's call this omega, and a boundary, all right, if you discretize the system of equations governing this, often what happens is that the values of u, right, your variable, at all the grid points within the domain and the boundary are often connected. So whatever is happening along the boundary affects what is inside the domain. So you have to treat the boundary conditions very carefully in this case. Okay, so that is on a short introduction to elliptic PDEs. All right, and so as we often do, what we do is we take a model problem, discretize it, and then we'll look at some examples of how you solve elliptic partial differential equations. So we consider the Laplace equation, which is given here. X and y are in the domain omega, and then omega is just the unit square. Okay, in this case, note that we are leaving out the boundaries for now, so we're just considering what is inside the unit square. And then you cover the square with a mesh, all right, of equal sizes, j intervals. Okay, the number of intervals in each direction is j, so that delta x, the distance of each mesh, right, grid, is given by 1 over j. Okay, now you can straightforwardly right, discretize this using the central differences for both the x and the y, and if you do that, you're going to get this, right? We've come across this before. If you do that for y, you get this. Because delta x and delta y are equal, that is why I have delta x here. All right. If they were not, then of course this would be different. And so you can multiply through by delta x squared and then rearrange the equation, and then you get equation 5 here. All right. So equation 5 is the finite difference formula that you can use to solve the Laplace equation. All right. So I have just repeated that the same thing here. Now, one interesting way of looking at this difference formula is that you can often use what is called a compass point notation. Okay, so the stencil for this is basically that if you want to compute u at I and j right here, this formula says all you need is that you need a starting point, you need a point to the west, a point to the east, and a point to the north, and so which is very similar to the compass points. And so instead of uij, you can often just represent uij with, say, qp or phi p. Okay, so this becomes for qp, I plus 1j is to the east of ij, so we just represent it with qe, and then similarly for the other ones. So instead of moving around with I and j's, you can just use p, e, w, and s as the compass points. Okay, so from now on I'll often be using this mostly, and that is what I'll be using to do examples and stuff. So let's start with the model problem, the first one, and then see how the equations develop, and then we'll move on to the second example, which uses a Neumann boundary condition. So here's a simple example. So you have j is 3, right? So you have 3 intervals here, equal, and then equal. These are supposed to be equal actually in both x and y. So in this case, you have node 1, node 2, node 3, node 4. These numbers are the numberings of the nodes. So we only have 4 interior points. So basically, this equation here, this here or that, equation 5 here, would be applied to the interior points. All right. So what you do is we are going to assume that we know the values at the boundaries. So this is with the Dirichlet boundary conditions. We'll specify them later. For now, assume that we know what is on the boundaries. So what we don't really know and what we need to compute is the internal nodes 1, 2, 3, and 4. So you take point 1 and apply the formula to it, point 2, point 3, point 4, and look at the nature of the equations, and then finally you solve them. Okay. So this is a repetition of the same formula. So if I take node 1 here will be my QP, so I have 4 Q1. The point to the east of 1 is 2, so that's why I have Q2 here. All right. To the west of 1 is 6, so I have 6 here. To the north of 1 is 3, so you have 3 here. To the south of 1 is 16. So if you take node 1, the equation becomes what you have here. All right. And now note that we'll come to this, but note that 6 and 16, that is this point here, and that are known. They are the boundary points. So often you can take, we'll get to that, we can take this to the right hand side, and then we'll leave the unknowns on the left. And then you move on to node 2, and you do the same thing. Apply the formula. When you are at node 2, you're going to have 4 Q2 minus Q to the east of 2 is 13. So you have 13 here. To the west of 2 is 1, so you have 1 there. Right? To the north is given by 4, so you have 4. To the south is 15, so you have 15. And you do the same for the rest of the nodes, node 3 and 4. All right. So in the next video, I would just go through this, and then we'll develop the equations.